Hello everyone, welcome to the next section of the course, Building a Product Recommendation System. In this section we'll continue our project work in the e-commerce domain. Here we'll tackle the problem of personalization. We'll use machine learning algorithms to provide user-specific recommendations. Let's move on to the first video of this section that deals with understanding recommendation systems. In this video we'll focus mostly on our shopping behaviors. Also, we'll utilize each customer's unique behavior to provide a personalized shopping experience. Let's try to formally define a recommendation system. Recommendation systems, or recommender engines, are a class of information filtering system which analyze the input data to predict preferences of a user as they might have done for themselves. Unlike information filtering systems which remove or filter information, recommender engines add or rearrange the information flowing towards the user, which is more relevant to the current context. They existed in the form of our friends and family who used to recommend us things to buy because they understood our choices. These were, and still are, a sort of offline recommender engines. The web is full of online recommender engines, from recommendations related to who to follow on Twitter, to other movies you might enjoy on Netflix, to jobs you may be interested in LinkedIn. Recommender engines are everywhere, and not just on e-commerce platforms. Now that we've understood what a recommendation engine is, let's look at their different types. The first type is user-based recommender engines. They're also termed as user-based collaborative filters in general due to the extensive use of collaborative filters, specifically for such recommender engines. Another type is content-based recommender engines. These engines have the content or items as the central entities. These items are analyzed to extract features. Also, the user profiles are built to map user preferences to the type of items. The engines then use this information to predict items which are similar to the ones the users have liked in the past. Such recommender engines are also known as item-based collaborative filters. The next type is hybrid recommender engines. These systems take the best of both worlds to improve upon the prediction results. The two pure types can be used simultaneously, and then their results can be combined. They can be used for adding collaborative filtering capabilities to content-based systems, or even by unifying both the approaches into a single model. Hybrid recommendation engines are also better at tackling the problems which haunt recommender engines in general. Now let's discuss the issues with recommendation systems. Recommender engines are affected mainly by the two issues in particular, such as the sparsity problem. Recommender engines work upon user preferences or ratings for different items, depending upon the application to predict or recommend products. Another issue is the cold start problem. A special case of the sparsity problem is the cold start issue. In the first scenario, when recommending items to such a user is virtually impossible due to the unavailability of information related to his or her preferences. The second scenario is when an item is newly added to the system. The newly added item will not have any ratings by the users. Recommending such an item would be difficult for the recommender systems. Hence, these two scenarios represent what is termed the cold start problem. Very much like the sparsity problem, the cold start problem also plagues collaborative filters. Moving on to collaborative filters. That will be denoted as CF henceforth, and recommender engines in general use certain terms and definitions to formally define and tackle the problem. Collaborative filters are a popular set of algorithms heavily used across applications. These algorithms work on a simple assumption that similar users showcase similar behaviors. The algorithm assumes that the preferences or ratings of the other users in the system can be utilized to provide reasonable predictions for the active user. Neighbor-based collaborative filtering, also known as user-user collaborative filtering or KNN collaborative filtering. The KNN collaborative filter is used based on the core assumption of similar behavior amongst users with similar preferences. This algorithm makes use of similarity measures to predict and recommend items for the active user. The algorithm follows a two-step approach of first computing the predictions, followed by the recommendations. The three main components of this algorithm are discussed next. The first main component is predictions. The first step of KNN-CF is to make use of the ratings matrix, usually denoted as R, to calculate predictions. Since we are concerned about user-user CF, the neighborhood of active user, the user in consideration, denoted as U, is to be taken into account. The most common measure to aggregate preferences is to use the weighted average of n neighboring users. Mathematically, the active user U's predicted preference for item I denoted as PUI, is given as where UR is the active user's U's mean rating, S of U, U dash is the similarity measure between the active user U and the neighbouring user U dash. Another component is recommendations. Once predictions have been done for the active user, a recommendation list can be generated by ordering the items by predicted rank. This recommendation list may further be fine-tuned by applying certain minimal thresholds and other user-specific characteristics, such as preferences for colour, size, price sensitivity, and so on. Thus, this step generates a list of probable items which the user is more likely to buy based on his or her personal preferences. Next is similarity. A similarity measure is an important component of our collaborative filtering-based recommender engine algorithm. There are various similarity measures available for use. The most common amongst them is the cosine similarity measure. This approach represents each user as an n-dimensional vector of ratings, and similarity is measured by calculating the cosine distance between two such user vectors. Mathematically, cosine similarity is given as this equation, where vector RU norm 2 and vector RV norm 2 are the L2 or Euclidean norms for each of the ratings vectors.